Okay, I think we are good now, finally. So today's talk, reading the Zig standard library, because who needs docs? And the truth is, well, docs are not bad. Kinda having docs would be nice, but right now we don't really have a proper set of docs for the standard library. So the question is, what do we do in the meantime? And what I want to do is basically give a very, very quick, as quick as I can make it, rundown of all the things, how to get started at looking at the Zig standard library if you don't feel confident in doing this kind of thing. And also run through what I think are like the most common questions that one can have and see how we can answer them by looking at the source code. So yeah, let's get started. So first of all, there's a difference between the language reference and the Zig and the standard library documentation. So Zig has a, I think, also pretty good language reference, which teaches you how to do all the basic stuff with the language. But the language reference teaches you about the language itself, doesn't tell you much about the standard library. Maybe in some examples, some components of the standard library will be used, but that's not the point of the language reference. The language reference teaches you about how to do if branches, for loops, what are the types of variables that you can make, do you need a semicolon at the end of a statement or not, etc., etc. Well, the standard library documentation, it's just documentation of what the standard library is, and the language is a thing in itself, even without the standard library. Even though we normally consider the standard library an important part of the language, it's actually an accessory. So when we talk about the language reference, there is a language reference already available on the Ziglang website. Then that's what you're seeing here in the screenshot. It would be nice to be able to show you also the full URL. Unfortunately, it's not possible because Google decided that full URLs are bad. Let's show only domains. We're Apple now. And I don't like this. Also, Google is pushing AMP, which is a corrupted version of HTML. Then there's also a quick, which is another weird thing where they mix up what TLS, TCP usually do, but now they reinvent it on top of UDP. And I mean, if you look at this, it doesn't seem too bad, but then you look at this and you notice that quick is kind of stealing concerns from below and from above and boxing TLS in the meantime, in the middle. And I don't know, but at least you can say, well, at least they're doing this to increase speed, which is nice, right? We want the web to be faster. It's always too slow. Then at the same time, if you open a YouTube page, watching a YouTube video downloads the title 14 times to display it twice. Yeah, that's also that. So makes you wonder what's up with Google and the internet. Sorry for this rant. I don't know. I really needed to put this in the slides also because I don't know. It kind of feels like, you know, there's the web, there's Java, and then Google comes in and says, oh, it's for me, right? This was you made this for me, right? It's like, no, get your hands off this stuff, please. Also, I'm mentioning Java because, as you might be aware, Google and Java, Google and Oracle are have been heard by the Supreme Court of the United States recently, and was very interesting the things that they said. So Google is doing all these questionable API design work, and I mean, Google, I think, is famous for doing questionable design API, and then they have their lawyer go in front of the Supreme Court and argue that APIs, which they define as an interface, which is connective tissue between computer programs, which is at the most barely creative. They are in front of the Supreme Court arguing that there is no creativity in designing APIs. How dare you? Anyway, I don't want to pushed many bad words into this presentation. So I'll just say that I watched the full presentation, like the full series by Casey Muratori about Google versus Oracle. He's like listening to the entire recording, commenting it, and giving you also input on what they are referring to every time they refer to another case. I think it's a very interesting listen. It's multiple parts. I think it's 4 parts in total, kind of long each part, but it's worth it. If you wonder why an API should or should not be protected by copyright and what the hell lawyers by Oracle and Google are trying to make the United States Supreme Court do, it's like it's crazy, interesting, crazy, and I think also it's interesting even if you're not interested in like lawyer stuff much. But I think your programmer mind might enjoy it anyway. Anyway, enough of this rant. Let's go back on track. So I can show you the URL, but to reach the language reference documentation, you can go by clicking this beautiful link here, which is attached to every release. So master is the latest version. This is what we usually recommend people use, at least now that Zig is always still evolving. And there's a link to the documentation that you can find, and it tells you a lot of stuff. But it doesn't tell you much about the standard library. So for the standard library, what we would need is to have the Zig Auto doc system working, completely in order. And it is there. It's not completely broken, but it's not complete yet. And I think it's not in a state where you can really rely on it as you would with, I don't know, for example, the auto-generated docs from Rust. So this screenshot is what it looks like, and you might say, well, it kind of looks like the one from Rust a little bit. Yes, it does. I think a lot of the design ideas were kind of stolen from Rust, which I think is a good thing. And these that I'm showing here in particular is the documentation from my Zig OK Redis client. And yeah, it works. I rebuilt this yesterday, and actually no, today, and it still works. It's not bad. Some things are like some symbols are not resolved as they should, etc., etc. And so it's, how can I say? It's not completely broken, and but the problem is that development of the autodocs is kind of stopped until we move forward, until we put the self-hosted compiler in a working state, because then, like right now, doing more changes to the autodoc system that basically is based on changes to stage 1 is a bit of a waste, in my opinion. So I guess that's one of the reasons why this effort right now is not progressing much. So to give you an idea though, let's say you want to play with autodocs today, so you have your own small library and you want to try it out, you can do that. And the way it works is that it basically relies on 2 types of comments, / comments on top of a declaration, and / plus exclamation mark at the top level of a file that basically represents, let's say, a module, a package. And then you just run this command. So let me explain to you why this is Zig test. So you can do emit docs on test, or even compile exe, like build exe, or I think even on top of run. But the problem, the idea is, like, if you just want to generate docs, you don't care about the binary. So this is why I have no emit binary. And the reason why I'm testing is because Zig is doing lazy evaluation. So if you have an executable that it's not using everything inside your library, then the things that you don't use are not going to be referenced, and then they won't show up in the generated docs. While the idea is that your test cases should use, well, in general, should use more of your standard library, but more importantly, inside the test case, there is a very useful function inside meta, inside the meta namespace of the standard library, where there is a function called refer all decals, ref all decals, which means basically make sure that every declaration inside this type that I'm giving you is referred to so that it shows up in the documentation. And usually these calls are put inside test so that you use test to emit the docs and then you don't even care about the binary. As I was saying, like the autodoc system is still a work in progress. So, oh, it's not in std.meta anymore. Oh, it's in std.testing. Thank you, Joachim. Thank you very much. I'm being corrected live. Awesome. So why docs? Why do we need docs? Like, why people want docs for the standard library? And the answer is that because docs tell you stuff, teach you how to do things. They're useful. That said, to be honest, though, especially in the case for Zig, they are not like super necessary, especially when it comes to the standard library. Because as we will see, like if you think about it, given that the in any case docs would basically be the autodoc system which relies on comments, you can see these comments in the source code. So maybe is it really necessary? Well, maybe if your code is this, or I just put in this as an example of not perfectly readable code, but I might be thinking about, I don't know, Java docs or some other languages like that. Maybe in that case, reading the source code is way too much. But I think in Zig, you can actually go very far by reading the source code. So autodocs are going to be great when they are complete enough that we decide to really make them the main way of documenting code, but you don't need them, at least for the standard library. Because again, as I was saying, the standard library, maybe it's not perfect, but even if it's not perfect, it's still pretty damn good. And the code, in my opinion, is very readable most of the time. And on top of that, there are doc comments already there. So even if we don't have the nicely generated website with JavaScript that enables fast page transitions and full text search, you can still do a lot of stuff by reading the source code. So, but before we start, let me answer a couple of questions about the standard library. So I'll guide you through really the first steps that you need to take to get used to reading the standard library. So first of all, where's the standard library? And the standard library is inside the Zig repository under lib.std. So you navigate these two folders and you will find the root of the standard library. Then once you get there, how do you navigate it? Well, there is a common structure that basically is repeated for every subpart of the standard library. The main import point of everything is standard.zig. So whenever you do import std, you are importing the public declarations inside std.zig. Then each submodule, each subpart of the standard library has its own file. So for example, if you are doing std, so let's say you imported std, then you do std.math. This refers to what's inside math.zig. Or more precisely, std.math refers to the public symbol math, public declaration math exported by std.zig, but content of that namespace are inside math.zig. These submodules can also have their own folder in case, like some are trivial and only have a file, but some others are not exactly trivial and they have a bunch of stuff inside. And some of their declarations are in the main file, like the implementations are in the main file, but some other more like beefier implementations of, I don't know, types that they export or particularly convoluted functions, they are in separate files inside a folder with the same name. So math has its own math folder. Yeah, it's used when there's a lot of stuff. But the point is, regardless whether there's this folder or not, exports are wired in the main file. So whatever you might find inside the math folder, you will find it first referenced inside the math.zig. So this allows you to understand that you don't have to navigate everything, but you have to make sure that the files are the first thing that you check. And to wrap everything, be aware, every export has to flow from wherever the declaration is, maybe inside a file, inside a subfolder, but then it has to flow to its own main file, and then it has to flow into std.zig. So this gives you an idea of how things is organized in a hierarchical way. So while you are roaming the files, let's take a look. Let's see what you have to look for. So first of all, doc comments, of course, because they are giving you a human level explanation of what's going on. Then there are pub declarations. Search for pub declarations, because stuff that isn't pub is something that you cannot access. It's part of an internal API, and maybe you want to learn more about that, but how can I say? First, you should look for what you are supposed to use, and then if you want to investigate how the thing that you are supposed to use works inside, to better understand whether the parameter that you were thinking of giving makes sense or not, is correct, or there are some other preconditions that you need to meet to use the functions correctly. Then you can look into non-pub things. So that's why two important things to search for is pub.fn and pub.const. And by the way, source code in the standard library, unless somebody is being a bad person, but I think every single source code source file in the standard library has been always gets run through zigfmt. So you know it's gonna be you can rely on the fact that it's going to be just one space between pub and fn, and there's not gonna be like weird stuff happening around these particular combinations. So you can search, you can grab through these files. Final thing to look for is tests. I think Jacob also mentioned this in the previous talk. But yeah, take a look at tests, because when you find tests, they show you usage examples. So you don't have to overthink too much and test things blindly too much yourself. When something has a test, that will show you in a practical way how things are supposed to be used. So let's take a stroll through the standard library. And to guide our explanation a little bit, I prepared a series of questions that I'll try to answer, not completely, but I'll try to answer by showing you the relative code. And I hope I'm not going to mess this up, because there's quite a few things that I want to go through, and hopefully I'll be able to do so in a reliable way. So let's see if 3 questions first. So how do I compare to strings? How do I require an allocator? And how do I zero some memory? So let's see how to answer those questions. So there we go. So I'm in the Zig repository. I scroll down, I go into lib, I go into std. And here we go. First, I see the folders because they are put on top. And by the way, I'm doing this on GitHub. You don't have to do it on GitHub, right? You can do it on your computer. But I want to show you that you can even do this by looking on GitHub without having to fork to clone the repository if you don't want to. So folders, but then files. So every folder has an equivalent, a file with the same name. And the starting point is, as I said, of everything. So the sink of every pub thing that you can import is std.zig. So inside std.zig, there are some types. Symbols with an uppercase name are types, like hashmap, array list, hashmap, mutex, packed int array. And these are all imported into std, and these are types that you can use directly, thread, for example. But then there's also all the what I refer to as submodules, so all the parts of the standard library, like OS, net, mem, IO, JSON, right? And these are all exported. And here you can see, there you go. You're right. It's testing refl decals. This is the test that simply makes sure that if you try to build the documentation, every single thing present in here is going to be referenced so that it shows up in the documentation despite lazy evaluation of code. Okay, so let's try to answer our question. So we had compare to strings. How do I compare to strings? So strings, comparison of strings is inside mem. Mem has a bunch of things about memory. So there's a declaration. So it's exporting the allocator interface. So I said also another question from earlier was, how do I require an allocator? Well, you import allocator from here and you accept a pointer to this allocator in your functions. So this is where allocator is. But then you would say, well, maybe I'm more interested in seeing what's inside allocator. And you can do that. You can go inside mem/allocator and you'll find allocator and you'll be able to look what allocator requires and provides. So there's a validation allocator, which apparently it's a particular implementation of allocator. But let's scroll down very quickly by doing pub fn. So let's see, validation wrap, align, awklen, copy. Oh, this might be interesting. Copy all of source into destination at position 0. So these copies, given two slices of type T, right? It copies from source to destination. And it does the copy, and there are a couple of preconditions that you have to meet to use this correctly. Then there's copy backwards, which has different preconditions. Then set, then zeros. Oh, how do I zero some memory? There you go. There's zeros, allows you to zero any type. But read the documentation here. So generally, Zig users are encouraged to explicitly initialize all fields of a struct. Explicit is written twice. Rather than using this function. So in Zig, you don't zero stuff nilly-willy like you do in maybe other languages. But if you need it, it's here. There's also secure zero. So prevents the store from being optimized out. Next, zero, init, order, less than, equal. There we go. How do I compare to strings? Well, strings in Zig are sequences of bytes, which generally speaking, you can represent with slices, and equal basically compares to slices, and it tells you whether they are equal or not. So we answered basically, I think, all our initial questions, but let's take a look at what else we can find in here. So index of, span, span-z. Span and span-z are a bit advanced, so I'll skip them, but there's len. So this tells you the length of multiple types. And you know you can do slice.len or array.len, but this, I guess, it's also going to tell you the length of like null terminated, or more precisely, sentinel terminated sequences that you don't have the length written anywhere, so you need to scan them. In the sentinels, all equal, dupe z, so you can see, right, just by searching for pubfn, I can quickly scan through all the things that are offered in here. Let's move into another subpart of the standard library. So let's try to answer some other questions. So how do I get an allocator? Right, I mentioned earlier that mem exports the allocator interface, but what about the implementations of allocators? So where do I get those? And then also, how do I interoperate with malloc? Maybe these are other questions another question that you might have. So let's try to answer those two questions. So how do I get an allocator? And how do I interoperate with malloc? So let's go back. I know that this stuff is in heap because dynamic memory allocation is heap related, and that's just an arbitrary choice that the standard library made, right? But it's reasonable. So let's see what we have in here. Start from the beginning, and at the top, immediately we have a few pub-const declarations that are exported from something implemented inside the heap subfolder. So in here we have logging allocator, an arena allocator, and general purpose allocator. So this already actually answers how do I get an allocator, and the answer is you can get an allocator directly from std.heap. General purpose allocator is as the name says, is what you should be using normally. Arena allocator is an allocator that implements an arena system. So if you want to know what arena allocators are, there's a talk by Benjamin Fang. You can find it on the Zig SHOWTIME YouTube channel. But long story short, arena allocators, it's a chunk of memory, and you have a program that has a cyclical structure where every cycle you allocate some memory, but then at the beginning of the new cycle, everything that was allocated beforehand, you're not going to need it. Think web servers, think games. Every frame, it's a loop, right? And the arena allocator is very efficient for this type of system because the allocations don't really get allocated in random places in the heap, but there is a chunk of memory that gets used, and you start consuming it, and whenever you reset everything, basically you just reset the counter and keep using the same memory. So that's why it's a thing. Logging allocator, I'm guessing it's an allocator that provides you some logging, but let's go investigate. So inside heap logging allocator, let's see what it looks like. Very briefly, I won't go too much into it, and honestly, I've never even used the logging allocator, but let's take a look at if there's any documentation what it tells us. So this allocator is used in front of another allocator and logs to the provided stream on every call to the allocator. Stream errors are ignored. So you provide a stream like standard error, or maybe a file. A stream is a writer-reader interface, right, on top of a file descriptor of any kind. And then, so you once you have the logging allocator specialized for your stream type, then you can pass it a normal allocator, and every request to the normal allocator gets first routed through this outer allocator that makes sure to print that alloc was called, free was called, shrink was called, expand was called. So yeah, I mean, that's what the name kind of implied, right? So we know how to find allocators. That's nice. No, not event, sorry, heap. So the other question was, how do I interoperate with malloc? Well, let's take a look. There we go. Here there is the pubconst C allocator. So the C allocator is a allocator that, well, it fulfills the normal allocator interface. So you can pass it around to everything that accepts a pointer to an allocator interface, but it uses malloc inside. So to use the C allocator, you have to link against libc, and it calls malloc and, you know, all the usual C standard library, malloc, free, jazz. Why do you want to need this? Well, there are, I guess, a couple of reasons. One is if you are interoperating with a library, with a C library that is giving you pointers to memory that was allocated with malloc, and then you are supposed to take ownership of the memory and free it whenever you are done using it, you need to free memory with the same allocator that it was allocated with. So you can't get this pointer from the C library and then try to deallocate it using an arena allocator. That doesn't work, doesn't make sense. Like the allocation strategy is completely incompatible. But with this, you can interoperate with C more easily. So you get a pointer from C and you free it using the C allocator. Another reason to want to use this is if your program has to play nice with projects where at linking time, like when loading the executable, the implementation for malloc gets swapped out with another similar implementation, like a gmalloc, something like this. So I don't have recent experience with that type of stuff, but some people do, and that's how you do that. So I think we answered both questions. Let's move forward. How do I get standard in, standard out, and standard error? That's another good one. Well, if you watched my last talk, I think you should know. But let's try to answer this again. Standard in, out, and error are in I/O. Inside I/O, there's a bunch of declarations about mode, whether we are doing I/O mode or blocking mode. There's other stuff, but there we go. So look at this, get std out handle. That seems interesting, but it's not public, so we don't care. Then we go, found pub get std out. So this gives you a handle to the standard out, and it returns you a file instance. Standard error returns you a file. Standard in returns a file. And apparently to do, no, async IO on Windows doesn't work yet perfectly. It requires a dedicated thread. So you also learn about this, and there's a link to the relevant issue / pull request in this case. Well, that's interesting. So there we go. That's how you use this stuff. Are there any tests about this? Let's see. So I haven't showed you any tests yet, but no, it seems there are none. Let's see if, let's go back to mem. Or actually, you know what? Let's go back to heap where there were all the allocators. Let's see if there's any test. So test C allocator. There we go. Test C allocator. If we are linking with libc, this test runs, otherwise it doesn't do anything. And here's how you use the C allocator. Well, I mean, in this case, it's kind of obvious, right? You allocate, specify the type, specify how many you want of those, and then you free, it gives you a slice, and then you free it, and then if you want, you can also do realloc. And apparently, there's also the wasm page allocator, and this is a test for the internals. Page allocator, heap allocator, arena allocator. So you see, you can use tests to see how to use those. In the case of allocators, they are kind of obvious, I guess, but maybe other stuff isn't. So searching for tests is useful. So let's try to answer more questions now. So we saw that standard in, standard out, and standard error are files. So how do I open normal files, and also what's in a file? So let's try to answer those questions. So files, how do I open a file? Well, I think there are multiple ways. I know one. Maybe chat can tell me what the other main ways are. But if you look inside fs.zig, I believe, so there's a bunch of stuff up here about, so here's file. So file is defined. So one question was how do I open files? And the other is what's inside a file. So file is defined inside fs/file. So we'll go there later. But in the meantime, let's see what else is in here. Max path bytes, base64 encoders. Let's start searching using pubfn. Oh my god, pubfn. Okay. Atomic sync link, update file absolute, copy file absolute. Init of what? Of a atomic file struct. Okay, interesting. Make dir absolute z, so you can, make directories, rename directories and files and stuff. What's this? Oh, this is a directory struct. So the directory struct, I'll scroll down. It's kind of big, has a bunch of things inside of it. So let's see if we can move forward using pub. Next, iterate, close, open file WASI, open file ZW. Z is for non-terminated strings, W is for Windows stuff. And then there's WASI, make dir, make path, real path, blah, 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 a bunch of stuff. Rename. We're not here for this, so let's move forward. Okay, there we go. Here's the entry point. So there's open file absolute. That opens a file giving you, and you have to provide the absolute path. Same with Z for null terminated strings, or for the what the fuck 16 encoding that Windows uses for strings. You can also do create file, but here's what I think is considered the idiomatic way, unless you're trying to do something different. So if you don't have any particular way of opening a file and just want to open a file based on the current working directory, you just do fs.cwd. This gives you an instance of dir, and then inside dir you can use all these methods to do stuff, but namespace inside the directory, right? So you can do read file, and you provide the directory, and then you only need to provide the directory name instead of providing the instead of having to like compose and chain strings together and have to think about slashes, etc. So that's I think what is considered the idiomatic way, again, unless you're trying to do something different. So the directory object turns out it's kind of interesting. So you might want to take a look at the public methods that it exposes. Another question was, okay, what's inside file? So once I have a file, what can I do with it? Well, so for file, we need to go inside the fs directory, file, and here we can find the file struct. So it has a bunch of properties. One suggestion is don't look at properties too much. Start by looking at public methods, and the best starting point is init for stuff that has an init function. In the case of files, I think they don't have an init method / function because they are usually they're considered like kind of dumb structs, but they have close. They can check if something is a TTI. So let's start with the public fn dance. So close is a TTI. Does it support ANSI escape codes? set end position, seek by, seek from hand, seek to, blah, 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 mode. You can start files, right? So to get information about last, when it was modified last, etc., etc. Update times, read to end, read. So you can use this to read a file, but what's more important is, I think we'll find it later, read all. So read reads a bit, but it doesn't necessarily read as much as you wanted to read, while read all makes sure to read everything as much as it can. But there's also, so let's go down, pre, read v, read all. This is kind of advanced stuff. We don't need to look at it. Copy range all, write file all. There we go. This is the interesting stuff. Reader and writer. So dot reader gives you a reader interface. Dot writer gives you a writer interface. I go much into detail, but writer and reader are two important interfaces that basically are the generic interface that allows you to print into streams. And I think I'll go back, I'll circle a little bit into this later. But again, look at the advanced Hello World talk that I gave last Showtime, a couple of Showtimes ago. In that talk, I go more into detail on how these two interfaces work. So let's try to answer another question then. How do I open a connection? Let's see. How do I open a connection? So connection stuff is in net, but again, file first, not the folder. So inside net, there's an address. Let's continue with pub.fn. So there's an address, parse IP, resolve IP. So there's a bunch of parsing of addresses, I guess. Equality, IPv4 address. So this is IPv6 stuff, blah, blah, blah. We don't care for now. Connect Unix socket. So if it's a Unix socket and you have a path to it, this is what you should use. So you should use net.connect Unix socket. And look, it returns a file. So we know what a file is, right? And you know that from file, you can get a reader interface or a writer interface to use it as a stream. And there we go. There's also TCP connect to host. So this allows you to connect to a host, but it requires an allocator. Why does it need an allocator? Because to a name can correspond multiple addresses, and that's why it needs to allocate. But if you have the address, so if you don't need to do this step and you don't want to give it an allocator, you just have to make the address instance yourself and then pass it to TCP connect to address. No more allocators required. And you can use also the resolution step of get address list yourself. So this is where you do networking stuff inside net. Nothing surprising here, I guess. Let's move forward to other questions. How do I parse a number and how do I format a string? Let's take a look. So how do I parse a number and format a string? This stuff is inside FMT. Inside FMT, let's go with the pub.fn system. So there's format that has a lot of documentation, but I think you shouldn't care much about format because format requires a writer. And when you want to write to a writer, the writer itself exposes a print function that allows you to do a format print inside that writer. So the idea is that the writer represents a stream, so a file, right? You have stdout and you do stdout.writer, and this gives you the writing interface to write to stdout, and the same you can do with a file, for example. And there you will find print, and print will use this the mechanism implemented there. And there's a bunch of format things because format can format multiple different types and it tries to format them nicely. And so this is all implemented. So let's move forward. Okay, by moving forward, we cross parse int. So parse int is what we were looking for. How do I parse a number? There you go, there's parse int. So it takes a type and then the chunk of text that you want to parse and the radix and then it parses your int if it succeeds. And here you can see our examples of usage, right? So this wants to parse this string into a U32 and base 10. So this number inside the string is expressed in base 10. Let's see if there are other bases used as an example. No, in this test, all bases are base 10. Oh, well. Unless I'm missing something. I don't think I'm missing something. But you can see also that this test is also showing you that if you try to parse -10 into a unsigned number, this returns error.overflow, and this expect error as this. Also, apparently it doesn't like spaces, so you have to be careful about that. So we know how to parse an int. Let's move forward. Parse unsigned. So if you know that something has to be unsigned, you can use parse unsigned. Char to digit, digit to char. Oh, there we go. That's buff print. So how do I format a string? So the idea is, if you want to print to a string, you should use the writer interface. But if you want to print a string into a buffer and format a bunch of arguments inside of there you go. You have buff print. Basically, you have to provide the buffer. You have to provide the string that you're trying to to format, and the arguments that should be formatted into the string, and then it tries to do it. And another interesting thing is that you know that since you have to provide the memory, otherwise it would have to allocate, it also has to return a slice, because in case it doesn't use all the memory, it has to tell you up to which point it has printed the string and what, and because you know that from there to the end of the buffer, it's garbage data. But it returns an error. Let's take a look at the error. The error is defined here, and there is no space left. Well, yeah, makes sense, right? So if you try to give a buffer that is not big enough to really be able to fit everything, then it has to return an error. So as much as possible was written to the buffer, but it was too small to fit the printed bytes. And so you get this error. And maybe that's fine. Also, think about this. Maybe you just want to print strings in a buffer up to a certain length. Above that, you don't care. And then you ignore the error. So you can reason about these things, about the API, just by looking at the code. It's not too complicated. You don't even have to look too much at the implementation, right? You really can do just with the interface, with the signature and the error. And here you can see that what it's doing is actually using a stream interface that, a stream implementation that gives a streaming interface that is backed by a buffer, and then it's using format to its writer interface. But again, you don't care about this stuff. These are implementation details. So we know how to do buff print, how to do buff print z, count. Oh, and there's also alloc print. So we have buff print when we provide the buffer, but if you are fine allocating, then there's also alloc print. And alloc print has its own error that it can return, but in this case, it's just out of memory, only if the allocation fails. Otherwise, it succeeds because, yeah, it can decide how much memory to use. So that's nice. So I think we answered that question too. Is there anything else interesting down here? Oh yeah, comp time print. Comp print is also interesting. So sometimes you have both the format string and the arguments that are known at compile time. Then you should be allowed to do the formatting at comp time and just have a normal string that gets then turned into the executable, right? And that's what you get from comp time int, and that's nice. And here you have examples of usage, and there's also this set eval branch quota, which I'm not going to get into, but this starts with an @ symbol. That's a built-in I guess function. It's a compiler built-in, and you can learn about those from the language reference, but I'm not going to get into that in today's talk. So let's move forward. I think we are almost there. Only a couple of questions to answer. So how do I test stuff? We saw tests, right? But you want to write your own tests. And I mean, you should know by looking at this code and by reading the language reference that a test is just a block. Starts with test, has a name for the test, and inside there, as if it were a function, you write the stuff that should happen during the test. But yeah, maybe you want to assert something, you want to fail the test if two things are not equal, or you want to do similar stuff. So how do you do? Well, we saw already, right? std.testing.something. So let's go investigate inside testing. What's in there? So inside testing, oh, look, there's pubconst, there's a failing allocator. That's interesting. So you want to test something that takes in an allocator, and you want to make sure that it does work correctly and reports errors correctly. When an allocation fails, boom, use the failing allocator. How does it work? Go open the file, read the documentation in there, and see what the public interface is. But then it's not just that. There's also not only the failing allocator, but there should be also the testing allocator somewhere, I think. So, well, we'll find that later, but let's just scroll down the pubfn stuff. So expect error. So you give it an expression that returns a error union, and then you give it the expected error. And we saw this used earlier, right? And this makes the test fail if the error doesn't, so if the expression didn't return the error that you were expecting. Expect equal, expects two things to be equal, but let's see if they say anything about slices. This function is intended to be used only in tests. Yes, I think it's the same for everything in here. When the two values are not equal, prints diagnostics to standard error to show exactly how they are not equal, and then aborts. Nice. Expect within margin. This function is sent, okay, this first part we know, but it's interesting. So this is for like float numbers, I guess. Yeah, the types must be floating point. And there's a margin of error that you're fine with having. And by the way, this is very nice. I'm sure people that have used Go know how sometimes it's annoying that you can't do easily this kind of stuff. But at least I remember encountering this type of problem. So test expect within epsilon, expect equal slices. So this is for slices so that you compare type by type instead of just looking at the two slice pointers. Expect, that's expect for something that is generally something that should return a boolean, and the boolean should be true. Then there's a tempdir thing, so that if you have to make artifacts on disk, you can use tempdir, and I guess, yeah, it has a cleanup method that you just defer the cleanup, so you make sure that the directory disappears at the end of the execution. Oh, and there's a function. So this is the type tempdir, but there's a function. So I guess you call the function with a bunch of options, and then these functions creates the actual path on the file system, and then produces the type at the end. So that's what you should use. Except equals strings and ref all decals. Given a type, reference all declarations inside, so that the semantic analyzer sees them, and that's useful also for mainly, I guess, for documentation. So testing has a bunch of interesting stuff in there. Let's go. Final few questions. Power, log, etc. So these are math functions, right? Math functions, you probably know by now. And math, there's a bunch of constants that you can find, methods, and there we go. Ceil, floor, trunk, square root, log, log base 2, so log base 2, log base 10, natural log, etc., etc. So they're all here. And if you want to look at the implementation of those, you can go inside the different files. But I just want to point out one thing. These are also mirrored. Most of them are mirrored also as built-ins, but there's a reason why you might want to use the ones in the standard library rather than the built-in. So more precisely, let's find add. So add, you can do plus, right? Like you can do A plus B, but you might want to use math.add, because math.add returns overflows an error instead of panicking in safe release modes, like safe release, release safe and debug, or becoming undefined behavior in release fast. So you can use these to catch the error and decide what to do. And And same with all the other stuff. So that's why you might want to prioritize, in certain situations, add over alternative methods. So this answers that, I think. Next, hash map or set. Where are these nice data structures? Or like I'm used to dictionaries and Go in Python and Go maps. Where do I get this stuff? And the answer is inside, not hash, but hash map. Inside hash map, there's a few of these things. And actually, let me go back to std.zig. Hash map, we saw those in the beginning, right? Some very important types, you don't even have to import from their own modules because they are referenced directly inside std. So hash map unmanaged, and string hash map and auto hash map are all in here. So let's find out what's the difference between auto hash map, and you see that each one of those has the unmanaged version. Let's ignore the unmanaged version for now. So let's talk about a string hash map, a normal hash map, and a auto hash map. Let's learn what the difference is. And to do that, of course, we go into the corresponding file and we try to find pub fn hash map. General purpose hash table. No order is guaranteed, and any modification invalidates live iterators. It provides fast operations with quite high load factors, blah, blah, blah. For a hash map that can be initialized directly that does not store an allocator field, see hash map unmanaged. So this hash map saves our reference to the allocator inside. The unmanaged version doesn't, but this is a small detail that you normally don't really care much about for simple situations. So this is a normal hash map, but look, it requires you to specify the key type, the value type, a function to hash the key, and a quality function to test whether two keys are the same. And then there's also the max load percentage. So you have to provide a bunch of stuff, like you have to implement your own hashing function and your own equality function. That's annoying. So let's find auto hash map. Auto hash map, it's basically the same thing, but you only specify the key and the value, and it tries to automatically generate a hash function and a equality function based on the type. And you can look into these functions and see what heuristics they use. And the long story short is that basically you want to use this every time for everything except for strings. Because strings in Zig are pointers to sequence of bytes, right? Sequences of bytes. And if you use the most efficient, straightforward way of testing equality of two of these two things is identity, so checking if the pointers are the same. But that's not always what you want, right? Sometimes you are fine with identity, as in the same string, it's the same if the pointers are also the same. Some other times you need another type of equality where you want to actually compare every single byte inside the string. And that's what string map hash map does, because otherwise you might get tripped by the behavior of auto hash map. And you can see that it uses equal string, which does mem.equal, and it also provides its own hashing function. So for long story short, since I think 99% of all hash maps out there are actually string hash maps, use string hash map in that case. Otherwise, auto hash map is there for you. But if you want to get control over the finer details, then you can use hash map directly and fine tune every function and the hashing function itself too. Oh, right. Second question. How do I do a set? Well, I think I answered this already in a couple of other talks, but the answer is that you use hash maps, but you provide the value as type void. So it's a hash map that doesn't store values. And the nice, like in Go, you would use a empty struct, for example, as values. In Zig, it's kind of the same concept, except a bit more elegant, I would say, because when you specify the value as void inside the hash map implementation, the key value tuple, where is it? Let me find. So the entry, let's find the entry. So pub const entry. So entry has value of type void, and it uses 0 bytes of space. So that's really, really nice. And it basically becomes a set based on hash map based set without extra overhead. Two final questions. How do I get a linked list? Linked list, it's another data structure that I think is fairly common outside of arrays and hash maps, and linked lists are inside linked list.zig, but I think they're also exported from std directly. So let's take a look. I think we saw them earlier. We have singly linked list, so a linked list with a next, but without a prep, so you can go only one way. And then tail queue instead is the doubly linked list implementation. So let's take a look at those very quickly. L linked list. Singly linked list. It has a node that contains the data and points to the next node. And let's quickly read the documentation and then maybe see if there are tests and then move forward to the next type. So a singly linked list is headed by a single forward pointer. The elements are singly linked for minimum space and pointer manipulation overhead at the expense of big O of n removal for arbitrary elements. New elements can be added to the list after an existing element, blah, blah, blah. So it's a normal single linked list. And you can see the public methods. And you can see also that they have nice documentation in this case. And there's a nice test that shows you how to use it. Traverse forward, pop first, remove next, and then a bunch of expects. Tail queue. Tail queue, well, you can quickly see that the node type has a prep and has a next. And this explains the differences, and that's pretty much it. You can scroll down, find tests also for this type and see how they're being used. So that's also nice. And I guess we answered that question too. Final question. What if I want to do multi-threading? Where do I find multi-threading stuff? Well, multi-threading stuff is inside. Well, let's take a look at standard.zig. Do we have threads exposed there? Yes, we do. We have thread. So let's go find thread inside thread.zig. Thread.zig. And here we have pubconst thread. As I said, don't look at the properties, at the fields of the struct first, but start by the public interface. So I can tell you immediately that thread doesn't have a init function, but it has spawn. So pub fn spawn. This is the function that you use to spawn a new thread. I showed how to do that in a previous talk, which I think it's another thing that I showed in the advanced Hello World talk. But basically, you provide a type that has to be the input type of your function that you want to run in the thread, the function declaration, and then you can spawn a thread, and then it gives you a thread that runs, it's another thread, and then you can, let's see what can you do on a thread. Let's move forward with pubfn. CPU count, get current ID, so you can get the current ID of like a unique ID for the, well, not unique, but the ID of the calling thread. You can get a handle to it. You can wait. So wait is what synchronizes with a running thread, and that's it basically. So these are the things that you can do with thread. So there you go. That's how you run threads. By the way, people should veterans should see that I think this spawn interface is not the best, because basically if you want to pass a single argument to start function, like if you just need, I don't know, a string, you can say that this type is a slice of constant U8, and you pass that, and then that's fine. That's one, and then you give a start function that takes in a string, and that's it. But if you want to pass multiple types, you have to come up with a type that you define here, and then you pass in here. While if this, and you can see that I think this API was designed before tuples became a thing, because I think in newer Zig, what you want to do is this be any type, but then you say here that you don't want start function to be type of this. You want start function to basically have how many arguments it wants, but they have to match what's inside this, inside the tuple that you're giving. And so just use tuple and use the add call syntax to flat. So basically to use multiple, like a sequence of arguments, the tuple as separate arguments in the function call. Anyway, this is a small detail about API that I think should be renewed given the new features that we have in the language. So that's how you do multi-threading. And I think with that, I don't have any more things that I want to cover. This has been an hour-long talk. I apologize to everyone for the super long show time today. And yeah, that's it for today. So let me conclude just with one thing. Since I started ranting about Google, let me finish ranting about Google. So hi, Google. Since Google has been into trouble for using the Java SE standard library, and maybe Google is shopping for a new standard library right now, well, I'll let you know that you can copy this standard library. And also, as somebody that doesn't like Java on their phone, maybe next time no Java, okay? So please feel free to take inspiration. And that's pretty much from me. So that's the end. If there are any questions, I'll give people a couple of minutes as I catch my breath, and then we can move to the end of the show. Fuchsia. Oh yeah, Fuchsia. Is there no Java in Fuchsia? I hope so. I hope. Well, I don't want the JVM in my stuff, but more importantly, I hope so for Google, because if they keep using the standard library from Java even there, oh man, they're gonna pay so much. Oh, I don't think so. Okay, that's nice. That's good for Google. Let me drink a bit of Coke. I think they wanted to replace it with Flutter. Flutter, I think it's a GUI library, right? So they would have also to replace a bunch of other subsystems that are based on Java, I think. Fuchsia will support the entire Android runtime and running Android apps. So it has Java. It has to have Java inside. Oh man, they're gonna get burned so much by the Supreme Court, I suspect. Not good for them. Divine retribution, what can I say? Okay then, so since we have used so much time, let's